So hello everyone, I'm Fabio Cermelli, and today I will present you my paper, which is Conformer, that deals with continual learning in semantic and panoptic segmentation. So before starting, what is semantic segmentation? What is segmentation in general? So in segmentation, what you want to do is to cluster a region of pixels belonging to the same semantics. So for example, in the video you're seeing here, it's taken from cityscapes, and you see that each region of the image is being grouped. And for example, you have groups like cars, persons, vegetation, road, and so on. And image segmentation so requires to cluster pixels given their semantic. And there are three kind of tasks given the semantic you want to separate. The easiest one is semantic segmentation, where actually you want to assign a cluster for each class, regardless of different objects inside the class. So in segmentation, typically we have two kinds of objects. The countable ones, which are kind of people, cars, semaphores, whatever, that you can actually count different instances of the object. Or we have non-countable objects, which are called stuff. For example, sky, building, road are all non-countable objects, things that you cannot group in different instances. And semantic segmentation only can deal with every type of object, countable and non-countable, but it groups everything in just one mask, in one big cluster. There is instance segmentation, where you want to cluster different instances of the same classes in different regions. So for example, you can see in here that we have different instances, different masks for each of the cars and of the person. And finally, we have panoptic segmentation, where you want to do both. You want to provide a class for each pixel, and in the meantime, you want to differentiate different instances of the same class. So here you can see that we have different masks for each car and people, but we still also have the stuff regions identified by the blue and violet colors, which are sky and road. And in the recent years, we have seen a large improvement in performances on these three tasks. And it has been thanks to fully convolutional and transformer architectures and new datasets, of course. But from my point of view, all these methods that have been developed have still a problem. And the problem is that once they are trained, they are fixed forever. And I will show you why this is a problem. So let us assume that you want to deploy a model into an autonomous driving car. So let's say that you want to buy a model that has two classes, person and car. So you go to some vendor, you ask for the model, or you either train it for yourself. So you collect a data set, you train the model, and so on, and you deploy it. But after you deploy it, you realize that you miss some classes. For example, you want a model that is able also to predict bikes, but you spend a lot of money to take the initial model, right? So you don't want to completely buy a new model. You want to extend it on other classes without fully retraining. However, the retraining is the only solution that is available right now. So what you can do is that you discard completely the old model and you train a new model from scratch. So you start again with data collection, you do again the training, and you get the final model that has all the classes you want to see in your model. Of course, this is very expensive because data collection is, of course, an expensive process. Training is, of course, an expensive process. So you're wasting your money because you did it a few weeks before just to get the first model. So you spend twice the money. Another better solution is to collect a data set with labels for new and old classes and only fine-tune the starting model. So what you want to do is annotate, in this example, car, person, and bikes in the data set, and you want to fine-tune the old model to get all the classes. However, this process can be still expensive because in this small example, we have only two old classes, but in real-world use cases, we may have hundreds of classes. So annotating all the hundreds of classes that we have already in the model is redundant and is a cost that probably you won't pay for actually deploying a model. So the last solution is to collect a model only for the new classes. So you can see here in the example that we collected a model only for the bike class. All the other classes are not annotated. And we want to fine-tune our model to get all the classes that we have before, plus the new one. What's the problem with this approach is that if we just fine-tune the model on the new dataset, we are starting to forget the old classes. So we are good on the new class, but slowly we start to forget the person and the car. And our model will be able to predict bike, but nothing else. And of course, this is a problem. And this problem will be the main focus of this work. So there are a few works that try to address the problem of continual learning in semantic segmentation. And I'm proud to say that one of my first works was Modeling the Background that gained a lot of attention in the community. And now it has been cited by multiple papers published in top conferences. And so we have seen a lot of works on the continual learning for semantic segmentation. There have been BLOP, SSU, there was representation compensation network, and so on. But the real problem, from my point of view, is that all of these works were only able to operate in semantic segmentation. And they completely ignored the important instance and panoptic segmentation tasks, which are fundamental for real-world applications. So today, what I will show you is the first continual segmentation setting that is able to perform both semantic and panoptic segmentation. And we will not target explicitly instance segmentation because for us, instance segmentation is included inside panoptic because it's kind of a subtask. And we are the first to investigate continual learning for panoptic segmentation. I will show you a model which is conformer that is based on the mass-former architecture, which is a new architecture I will present you today, and a few losses to make it work in continual learning. And finally, I will show you the benchmarks on which we compare conformer with previous works, and I will show you that conformer is able to outperform them on different settings. So let me start with a bit of background. Let me explain you what allow us to make a single scenario for both semantic and panoptic segmentation. And the main contribution of mass-former was actually to have a paradigm shift in the semantic segmentation approach. So for semantic segmentation, in the last 10 years, we had methods that were able to classify each pixel by just extending the convolutional networks to predicting a pixel-level probability distribution. So we had the image, we just have the image, the image go through the model, we get final per pixel class predictions, and then we have the simple argmax that has been optimized with a cross-entropy loss, which is actually classification done at pixel level. What mass-former presented is a huge paradigm shift, because what they say is that we can get rid of pixel-level classification, and we can predict up pairs for the final prediction, and the pair is made of a binary mask and a probability distribution for the classes. So you can see here that we have n queries, where n is typically 100. So we have 100 predictions, and each prediction is made of one binary mask and a cluster probability distribution. And in this example, you can see that in the first mask, we have, for example, the building. In the second, we have the sky, and we can have different classes. And in this way, you can deal with different segmentation methods, segmentation tasks, sorry. Because if you want to do semantic segmentation, you can just cluster all the objects of a class inside a single mask. If you want to do panoptic segmentation, you can just have multiple masks for different objects of the same class. And so in the end, you can deal with all the tasks together without any change in the loss, architecture, or whatever. So how can we do mass classification with a method, of course? So I will present you the architecture. And first of all, we have backbone. The backbone can be any image classification backbone, like ResNet or DIT or Swine, whatever. And the feature obtained by the backbone are then passed in a transformer decoder. The transformer decoder gets an input, the image features, and the n learnable queries, and output n per segment embeddings Q. So each per segment embedding, you can imagine it as something that represents an object inside the image. And the goal of the transformer decoder is taking the queries as input and output the refined query. And of course, each one should represent something in the image. Then we have the pixel decoder, The pixel decoder takes the image features and extract a per pixel embedding. So the goal of the pixel decoder is actually provide a high resolution feature embeddings so that we can get good semantic segmentation, good segmentation predictions. So after we have these two outputs, what we can do is to merge them to get class probabilities and mask binary masks. The class probabilities are obtained by applying a classifier to Q. So each per segment embedding is then classified independently by a classifier, and we can get a probability distribution for each one. The probability distribution, of course, is on all the classes, and but we, of course, have something more than the classes we want to see, because we also have the void class. Since we are overestimating the number of classes that may appear inside the image, what we do is that we have the classes, but each query has also the probability to predict void. So something indicating there's nothing inside this query. That's not an object, you can ignore me, something like this. The binary masks are then obtained by multiplying the per segment embedding Q with the embeddings, the per pixel embedding. So they are just multiplied together and binarized using the sigmoid activation. So you can have multiple masks being active with at the same pixels. And of course, you can get the final prediction just by looking at both the mask and the class probabilities. I hope it's clear. If you have any question, you can stop me and we can discuss about that. I will go ahead on the training of Masterformer. So to train this model, of course, you need labels. And the labels are in the form of a binary mask and a class label. The first thing you need to do is to match your queries, in this case, 4 queries, with the labels. For doing this, we use the Hungarian matching algorithm, like in Detter, where basically we compute the loss for each permutation of the query and the pseudo labels, and we get the matching that gives us the lowest loss. In this case, of course, it's like using the first prediction with the first label and the third prediction with the second label. After we do the Hungarian matching, we simply have 2 losses: a classification loss that is applied on each logit, and a mask loss that is applied on each matched mask. So in the classification logit, you can see that it is a simple cross-entropy loss that optimize the class if there's something matched, or optimize the void class if there's no match with the query. On the other side, in the mask loss, what we do is that only for the matched masks, so masks that are not matched are not trained, but the ones that are matched are trained by using a binary cross-entropy loss and a dice loss, so that to minimize the differences between the label and the prediction. And with those 2 losses, we can train Masterformer. Okay, but how can we transform Masterformer in something that works in continual learning? Before starting, I need to say that Masterformer, of course, is so state-of-the-art on all the segmentation tasks. So it has been shown that Masterformer was state-of-the-art on Panoptic, instance, and semantic segmentation. Okay, so what I was saying is that before going on, I need to introduce the setting. So since we are in continual learning, what we want to do is to perform multiple training steps. And each training step should include a new set of classes. So in the first training step, we include classes N1 using a dataset D1. In the second step, we include classes N2 on a dataset D2, and we want our model to predict all the classes seen so far. And this process can be repeated many, many times until step T. What is important to say is that only the current dataset is available to the model to learn the new classes, and we cannot rely on the old datasets. And this is a very strict scenario, but it is what often happens in the real world. Because when you have a model, when we have a dataset, either you both it from some vendor. So for example, you both a model, an initial model, and you both a model, and you don't have access to the data on which the model was trained because the company training the model does not release it. Or maybe in other domains, like medical images, you have privacy constraints. So you cannot use other patient's data for your training your model. You cannot store them and so on. So we will work on the setting where no old images are available, and you only can fine-tune your model on the new dataset. And finally, as I said before, the table is composed of a set of pairs made up by the ground truth class, which is, for example, car or person, and the binary mask associated to it, indicating where is the object. So when you see the white in the label, it means that the object is there, and the zeros means that the object is not there. So I have reported here an example of the setting. Let's say in the step t-1, we want to learn the car. We have annotation only for that class. We don't have any other annotation. We want to feed this annotation, the image, to the model, and we want that the prediction closely match the annotations. But when a new step comes, for example, on the step t, we want to learn the person class, and we have annotations only for the person class, even if the car is inside the image. So we want our model to learn the person without forgetting the car. But what happens often in continual learning is that if you just fine-tune your model, you will forget the old classes. And that's called catastrophic forgetting. So all the continual learning community focus on preventing the forgetting by adding some regularization term to the model. And in the next section, I will show you what we did. So let's go to the method section. We started from, as a framework, we started from one of the most flexible and used approaches in continual learning, which is knowledge distillation. What we do in knowledge distillation is that before fine-tuning the new model, we copy and freeze it. So we can use it as a reference for regularizing the training. So in this example, we have the student model in blue and the reference in gray. So we can use the student, the blue one, and we can teach with the gray one how was it able to predict the whole classes, so that we can constrain the two models to be similar, so that we prevent forgetting. But the real question is, how can we use the teacher to regularize the student in master forward? Because with all methods like per pixel classification or even image classification, what we do is just let the student mimic the output distribution of the teacher. So if we have a probability distribution over the classes, the student should only match this probability distribution. But here, with this kind of outputs, it's different, because we cannot just say we want to constrain the probability distribution, the final probability distribution, because we don't have one. We have a set of masks connected to a set of probability for the classes. So we started investigating what can cause the forgetting here and where we should focus. And we found that actually the mask doesn't suffer forgetting, while the classification is the problem. Why the mask part don't suffer forgetting? Because as I said before, only the matched mask is actually trained. So if we don't train all the other masks, what happens is that the model tries to keep constant as before, so there is not much change in those queries, so that there's not much forgetting. Where the forgetting happens is, of course, on the classification part, because if we train our model to predict the person and we force all the other queries to be void, then all the queries will be void, and we will forget how to predict the whole classes. So the first thing we did is to investigate a way to regularize the classification part. And we proposed the adaptive distillation loss, where, of course, we want the student to mimic the output of the teacher only on the informative queries. So let me just show you what's a standard distillation loss. Sorry. So a standard distillation loss would force the student to mimic each of the teacher outputs, minimizing the Kullback-Leibler divergence. So you can see here in the question that we have the all class probabilities for the input query I and the class K, and we have the probability for the student model for input query I and class K. And if we just maximize on each of the queries, and n is the number of queries, if we minimize the distance on each query, what we are doing is probably we are giving the same weight to each query, right? So we are using a lot of queries that actually carry no information because they're void, while the only one that actually carry information will not have the strength to be remembered by the model, because we may have 99 void masks and one car query, and we want that car query to be more weighted than the others, right? And so what we proposed is very simple. We just said, okay, so instead of using a standard distillation loss weighted, applied on each query independently, we want to use a weighted distillation loss. And the weight was given by the value of the void class. So you can see in the equation here that we given a weight that is the proportional to the inverse probability of the void. So if a query, for example, the car here, has been predicted, is far from void, right? Because the probability of void here is mostly 0. So this is weighted 1. For the others, for example, this one, the probability of void will be mostly 0. So we don't want to use this query for distillation. And you can see another benefit of this approach is that we are not forcing the new model to predict exactly what the old model was saying. So in this circle, you can see that if the old model wanted to predict void on a query, and the new model is learning a new class on the same query, we are not forcing the new model to predict void. But we are saying to the new model, you can learn the new class and ignore what the teacher was saying for this. And I mean, this is very important to avoid interfering between new and old classes. So I will go ahead. If you have any questions, stop me whenever you want. The second contribution we had in Conformer is that we understood that mask-to-former sigmoid activation for the mask part was not fit for incremental learning. And I will show you why. So basically, if you use a sigmoid, as I said before, you can have multiple pixels which are active on different queries. So for example, here you can see the dog and the cat, and you can see that they have both a similar mask, and most of their pixels are overlapping. And so if we have something like this in the model, during the matching process and the distillation process, we will have that maybe the first query will be assigned to the new class, which is dog, and will be maximized to learn the dog class. And it's totally fine. But what happens also is that the old model will predict cat for query 2. And in the query 2, we have something similar as a shape of the mask. We are not training the mask, so the mask will be mostly the same at the end of the training. But we are training to the distillation part. So the old model was saying cat. And so now we have a model that is able to predict on 2 different queries the same shape and different classes. And so at the end, we don't know how to say, because the model is saying that on both pixels, we have 2 classes. And probably we just pick the most probable one, the most confident one, which is the new one. And we start forgetting the old ones. And what we do for avoiding this problem is very simple. It's just using a softmax. Because if you use a softmax activation on the queries, you totally solve the problems. Now only 1 pixel can be active at any query, and all the other query cannot predict the same pixel as the same shape as the dog in this case. So we totally avoid the problem of class interference by just using the softmax activation. And I will show you later in the ablation study that this was crucial to operating in continual learning. So finally, I showed you how to avoid the forgetting classification part. I showed you how can we avoid class interference with the softmax. But we are still not exploiting the fact that all classes may appear in the image button labeled. So I'm saying before that in this example, for instance, there is the car, which is not labeled. And of course, we can make use of it by using a pseudo-labeling approach. So we use the old model to extract pseudo-labels of the old classes, and we directly introduce the pseudo-labels inside the ground truth annotations. So in this case, we are not matching anymore only the new class, but we are matching both the new classes and all the pseudo-labels get from the teacher model. Of course, the pseudo-labeling is not totally naive because we do some filtering. We get the most confident labels. We try to avoid cases in which the old model is predicting the same pixel as the new one. So after this filtering process, we get the final pseudo labels, and we can use them and rely them as ground truth. So wrapping up, conformer is a method proposed by three main novelties. The first one is the adaptive distillation loss. The second one is a softmax activation for the mask predictions. And the third one is a mask-based pseudo-labeling. Now, after I introduce the method, let's see some experiments. And the first benchmark, of course, I want to show you is on semantic segmentation. So basically, we just cope with the same setting proposed in previous works. We use the ID20K dataset, which is made by 150 classes and 2,000 images taken from common scenes, so both indoor, outdoor scenes. And you can see that each pixel of the image has been annotated. And this is for semantic segmentation. So we have one single mask for different objects. We use the same continual learning protocols for previous works. So we had three different data splits, class splits maybe. The first one is 150. So basically, the first training is made of 100 classes, and the incremental learning step is made of one step of 50 classes. We have the 110, which is made of 5 incremental steps of 10 classes. And we have the 105, which is made of 10 incremental steps of 5 classes. So you can see that the first one should be the easiest one, because it has only a 1 incremental step with a lot of classes, while the last one, the 105, should be the hardest one, because it's longer and there are a few classes in each training step. Finally, we are using as a metric, we are using the intersection over union. So the intersection over union is computed for each class independently, and it's measured as the intersection between the prediction and the ground truth divided by the overlap, the union, sorry, between the prediction and the ground truth. So when they perfectly overlap, we have an intersection over union of 1, because the intersection is exactly as the union. And when we have a wrong overlap, so they are totally disjoint, the intersection will be 0 and the union will be still huge. So we have an intersection over union of 0. Since it is computed for each class independently, what we do is that we make an average over the all classes, new classes, and all the classes independently after the last incremental step. So we train the whole continual learning schedule, and after the last step, we just get the average. And now let's see some results. So for semantic segmentation, we reported few baselines. There is MIB, which is my previous works, both with DeepLab architecture, which is a semantic segmentation architecture, and our same architecture. We re-implemented completely MIB on the same architecture. And also PLOP, which is another work from my co-author, which is both from DeepLab and from the same architecture as us. The first set of experiment is on one step. You can see that fine-tuning is completely forgetting the old classes, the leftmost column, while it is able to learn new classes properly. In terms of all classes, you can see that conformer is the best one across all the methods, and that the other two methods had closer performances between the DeepLab and conformer architecture. Then we have the multi-step approaches settings, where you can see that fine-tuning is still working very bad for the old classes, and also for the new classes, the performances drop. And that conformer is able to get very good performances both on old and new classes. In particular, you can see that conformer is able to get the best, or mostly the best, performances on the old classes. There is also only PLOP, DeepLab, which is comparable on the old classes on 110. And the best results, or mostly the best results on the new classes, because it was comparable with PLOP on conformer. Anyway, overall, it got the best performances on the multi-step approaches. I reported here also a qualitative results. Maybe it's not super, it's not the best one, but you can see that we are able to predict all the classes inside the image, mostly as the ground truth. And as a second set of experiments, we have a benchmark on Panoptic Segmentation, which is a new one. We wanted to rely on a similar setting to semantic segmentation, so we wanted to use the same datasets, Of course, in this case, we have an annotation where different object instances are separated. So we wanted to predict object instances separate from each others. We have the same continual learning protocols, so 150, 110, 105. And we have a different metric because in Panoptic Segmentation, we use the Panoptic quality. Panoptic quality, as the mean intersection over union, is computed for each class independently and then averaged on the all classes. So we made the same trick of before. We made an average for all new and all classes after the last incremental step. I would just go fast in the metric, but what you need to know is that it's composed by two different metrics. The first one is the segmentation quality, which basically measures the segmentation quality of the segments that have been predicted correctly. So if I'm able to predict a mask correctly, I want just to know how good I was in segmenting it. And then we have the recognition quality, where basically we measure how good we are in recognizing the objects inside the image, but not in terms of segmentation, just in terms of recognition. So are we able to recognize all the objects inside the image, or we missed something? And this kind of quality is more close to image classification, where we just want to know if an object inside the image or not. Okay, results. Since DeepLab is not fit for Panoptic Segmentation, we reported baselines only on the same architecture as ours. And you can see that Conformer is able to outperform all the needs in all the settings. And what is notable is that the performances on the all classes are 6 points better than Plop in both 110 and 105, indicating that our model was able to learn the new classes without forgetting the old ones, and that the performances on the new classes is always comparable with Plop. So actually, we got the best results overall, and on the multi-step settings, we got 3/4 points better than Plop. Here, I have also some qualitative results on Panoptic Segmentation, and you can see here that windows are predicted separately from each other, and we are able to predict both three windows with different colors, even if it's not so visible that are different, and so on. Okay, as I promised before, I have an ablation study where we show the differences between using Mastoformer, so the sigmoid activation, and the softmax activation of Conformer. So I will show you the results on every setting in both Semantic Segmentation and Panoptic. And in Semantic Segmentation, you can see that while Mastoformer is able to get very close performances with respect to the new classes, on the old classes, Mastoformer was down of 6 points on the 105 and of 4 points on the 110. And this is a very important result because actually show that using the sigmoid activation leads to forgetting. But even worse in Panoptic Segmentation, because you can see here that we have a difference of 6 points in 110 for the old classes and 7 points for the new ones, while for the 105, we have a difference of 10 points in the old classes and 10 points for the new ones. And that means that without the softmax activation, it will be impossible to use Mastoformer in a continual learning setting. And I mean, of course, we had some issue to get through the review process with this contribution, because a lot of reviewers just said, okay, but it's like a slight modification. But I want to mention here that most of the time, a very simple modification like this one requires a month of study. So we had a lot of works to understand that sigmoid was a problem for the model. And you can see that with sigmoid, nothing is working. So often, a simple modification are valuable contribution. And I hope that these ablation studies show that. And the final ablation study is on the loss functions. So I wanted to show the different performance of the model with different losses. So we start from fine-tuning, where we are not doing anything. So those are the results of before of fine-tuning. And then we have the adaptive distillation loss, where we just use the adaptive distillation. And you can see that the results on the old classes improves a lot, but we have a little drop on the new classes for the 150 and a little gain for the 110. Using only the pseudo labels improves largely the results, both on new and old classes. And you can see that the performance is on 100, so on the old classes, was better than 12 points with respect to the distillation loss on the 150, and by 7 points on the 110. However, if we combine pseudo labeling with the standard distillation loss, it doesn't improve too much the performances. It gains a few points on the new classes, but the performance in the old classes doesn't change. But if we mix it with our proposed loss, the adaptive distillation, you can see that we are improving the performances on the old classes by 6 points in the 110 and by 0.6 in the 150, meaning that a good adaptive distillation is mandatory for this work. And this concludes this presentation. Summing up, what I presented is a unified task of continual learning for semantic and Panoptic segmentation, and it was the first attempt to do so. And we presented a new approach, conformer, based on mass-to-former, that surpassed previous works on both tasks. As a future work, I think it will be nice to have, first of all, on the benchmark, both object detection and instance segmentation. And actually, I was happy to see that at CVPR 23, there was a paper that was using DETRE for continual learning in object detection, and they found very similar results to mine. So probably in the future, they can also be mixed up for a unified continual learning in object detection, instance segmentation, and panoptic segmentation. Another interesting thing may be comparing different architectures, because we started with mass-to-former, and there are others which are close to it, like mass-former, the first version, but also K-Max, DeepLab, and other architecture like this. So it would be interesting to understand how different architecture behaves in continual learning. Maybe there's no change, but maybe some architecture is better than others. And lastly, one thing that's I worked a lot during my PhD, I think it's very important for computer vision research, is reducing the amount of supervision. So learning new classes from just points or bounding boxes or image level labels would be very interesting, because labeling in semantic segmentation is one of the hardest and one of the most expensive part of the process. So if we can get rid of some of the supervision, it will be very nice for real-world applications. And with that, it's all. I want to thank you for the attention, and if you have any question, I will be really happy to answer you. Oh, maybe there's one in the chat. Can we call incremental learning a special type of fine-tuning? Yeah, I think so. I think continual learning is a special type of fine-tuning. Because basically what you want to do is to fine-tune the model on a new set of classes that you didn't see during the first training. And I think it's also interesting to see the development of continual learning for domain, when you have a change of domain. So maybe you train your model on something like a synthetic dataset, and you want to extend your model to a real-world dataset, or using other weather conditions or this kind of stuff. So yeah, I think it's a special type of fine-tuning, but a very interesting one, because you have very different challenges with respect to naive fine-tuning.
I have another question. So what if we just use the current model to so for example, if I want to add a new class and I have I have a good amount of data set for that class. But if I fine-tune it normally, it will forget the previous classes, right? So what if I use my current model to label the data set alongside that new class in that new data set? So how will that affect?
Yeah, that's basically the concept of pseudo labeling. But actually, what happens most of the time, and that's why you need the distillation losses, is that it's not always the case where you have all classes in the new dataset. So, for example, in autonomous driving, maybe you collect a new dataset only for bikes, and doing so, it's not mandatory that you have pixels of bus, for example, inside the image. So even if you label everything inside the image, you're not guaranteeing to remember all classes. And that's why using a distillation loss improved the results, as shown in the last ablation study. Because actually you can correlate concepts, right? So maybe your model will not see any bus, but will see a car, and it remembers that the car was similar to a bus. And so if it mimics the prediction of the old model, will keep the probability of the bus maybe a little higher than the others, and it should keep this probability a little higher than the others in the next step. And they've shown in a lot of works before mine that this helps in avoiding forgetting.
Right. And I think the new parameter efficient fine tuning methods that were adapted from NFP, like Dora or adapter tuning. When I was reading about them, one thing I read that they are pretty helpful against catastrophic forgetting, because you're not changing your original model, you're just adding a small tunable adapter. So how do you think that can help in like continual learning?
So adding parameters to the model, was always been a bit of taboo in continual learning. So a lot of works were not they said, okay, if you're adding parameters, you're cheating with respect to other works. So this kind of trend of adding parameters was a bit ignored by the community. I think there are cases where you can actually add some parameters, like in the case of adapters. If you need to do very few steps, incremental steps, you can use additional parameters probably. And there was a work actually that was presented last CVPR, CVPR 22, that was showing that if you add parameters and then prune the model, you can keep the same number of parameters, but you improve a bit the performances. So of course, introducing parameters is helpful, but it was been a taboo in the last few years in the community. So to avoid like being criticized too much from reviewers, we stay away from that. But I think in real world application, it may be very interesting.
If we don't have any other questions, then I think we can end the session here.
Okay, if you have any questions later, you can just write me an email. I mean, you can find me on the website or whatever, and we'll be happy to answer you.
Yeah, thank you so much for the session. I really enjoyed it. Thank you for your time.
Thank you for inviting me.